Okay, great. So today Slava will tell us about perturbative.
Hey, Tom, I can't hear you. Hello?
We can hear you well, Slava. So I think.
All right, so it might be, the problem must be on Tom's side. Okay,
Yeah.
Hi everyone. It's great to be speaking to this audience. So it's a Bootstrap audience, but this is going to be a talk about RG, more specifically non-perturbative RG. And I'd like to start with a confession that for a long time, when I was a graduate student and I was a postdoc, I actually had a very low opinion about non-perturbative RG. I just thought it was a bunch of uncontrolled approximations and truncations. And this opinion was influenced by my PhD advisor and by various other physicists whose opinion I greatly respected. And in those days, CFT was something that was very beautiful and was reflecting the pre-established harmony of things, while RG was something dirty and human-made and so basically not up to the same standards. But gradually, I realized that this point of view is actually cannot be correct for various reasons. And okay, I'll state them in certain order that is not necessarily the one that I acquired all these reasons. But to begin with, not all our renormalization group fixed points are expected to be conformal. And so in this sense, the renormalization group is more general than conformal field theory. So by the way, please do interrupt me at any moment, because this is going to be kind of a weird and freewheeling talk, and so I expect some interaction. So the second thing is that we usually we like to draw this sort of pictures. When we have some UV and then we flow to the CFT and IR, and actually these sort of pictures, for me, they are basically the only way to understand why certain complicated CFTs exist. So for some simple CFTs like minimal models, you can say that, okay, we can just classify them. But why something as weird and complicated as 3D using model CFT exists is just it's a totally messy theory with a bunch of operators. There's just no, as far as we know so far, there's no structure to it. It just exists there. Okay, we can constrain it. And the renormalization group seems to be the most economical way to explain why such beasts exist. So, okay, just to introduce some terminology. So for me, what I mean roughly by non-perturbative RG, I mean some sort of Wilsonian RG flow where we're dealing with an effective action, which depends on the cutoff scale, S lambda of phi. And in perturbation theory, we can work with the bare action, with the UV action, which contains finitely many terms, finitely many relevant and marginal interactions. But in non-perturbative RG, once you agree to deal with the Wilsonian action, you have to work with infinitely many irrelevant terms, because they're going to be generated by RG flow. And sometimes when we teach students, we say that, okay, RG irrelevant terms, they flow to zero in the infrared, but we know that in the Wilsonian sense this is not quite true, because at every RG step, so if you have some irrelevant coupling, G irrelevant, then at every RG step it's going to be suppressed by some amount because it's irrelevant, but then it's going to always get a little bit a small kick from various other diagrams which contribute to this coupling. And so as a result of this, gets suppressed a small kick, gets suppressed a small kick at the fixed point. Also, infinitely many relevant couplings, they're actually non-zero. They may be small, but they're not necessarily zero. So this is clearly a complication, and that's why, in fact, all physics realizations of non-perturbative RG, they say, okay, what you can do in this situation, you have to truncate. And so depending on how you truncate, you get different results. So it looks indeed like a non-controlled approximation. But realization group classics, starting with Ken Wilson, they really thought first and foremost in terms of non-perturbative RG. So for them, this Wilsonian non-perturbative RG came first, and then perturbative RG in terms of epsilon expansion and dim reg, it was just some kind of trick which gives the same results, but it came second. It came after the non-perturbative RG. And so if you would like to look at the historical account, then for example, you can look at the section 4.5 of Wilson and Kogut review, which first explains RG in this Wilsonian way. And then they say in the next section that actually, if you just want to compute critical exponents, you can do Feynman diagrams and dim reg. But nowadays, we often only learn dim reg. We never even learn this non-perturbative RG in the Wilsonian way in detail. Another thing that you might want to look at is the section 6 of another review by Wilson, Reviews of Modern Physics. So this does non-perturbative realization group for the two-dimensional Ising model working in the space of 217 coupling constants. So it's actually quite mind-blowing that Wilson could do it in 1975. Well, the classics thought this way, and actually mathematicians, they still think about the realization group in this non-perturbative RG way. And in fact, non-perturbative realization group, it was used to prove dozens of theorems by mathematical physicists. So I give here a very partial list of things that people are able to prove using RG ideas. Well, for example, you can prove the three-dimensional confinement in U1 gauge theory. You can prove various stabilities of Gaussian fixed points like lambda phi to the fourth in 4 dimensions, or the Goldstone fixed point in the sigma model. And even you can construct, you can prove that the Young-Mills small finite volume is rigorously asymptotically free, 4-dimensional Young-Mills. And so all these theorems are proven without any truncation and approximation. So in fact, it is not true that non-perturbative RG necessarily has to involve truncation approximation. So given that mathematicians can do it, so mathematicians prove theorems, they are more interested in proving some structural results. But you could also say that given that they can prove some theorems, so they have some tricks how to construct, to control this non-perturbative RG. Maybe we could take those tricks and we can take this mathematical wisdom and we can actually use it to compute something. So for example, perhaps a dream would be that perhaps we can use this to set up a rigorous non-perturbative RG calculation for the 3-dimensional Ising critical exponents. And I actually believe that this is something that can be done, and I believe it will be done within the next few years. And if it is done, then perhaps realization group may again surpass Bootstrap in the accuracy of the critical exponent. So I think the game RG versus Bootstrap, the competition RG versus Bootstrap, is still going on, and it's not clear who is going to prevail in the end. But if one is willing to pursue this dream, which by the way, currently this is a wide open problem. So currently there's no rigorous result about three-dimensional easing fixed point. So we don't know if rigorously if it exists. If it exists, then it should live in some Banach space of interaction. So we don't know this. And if one wants to think about this sort of problems, then the first step is that one has to understand what has been done by mathematicians. And it's not very easy to penetrate this mathematical literature. So one has to bridge this gap. And so this brings me to the recent paper that we wrote in collaboration with Alessandro Giuliani and Vieri Mastropietro, who I hope are in this audience. And actually, Alessandro and Vieri are the experts in this mathematical theory of organization group. And so for me, it was a privilege to be able to collaborate with them on this project and to learn how this all works. And so the point of our work was to start bridging this gap. And to do this, we presented the simplest organization group flow where a non-Gaussian fixed point can be shown to exist without any truncation or approximation. So you have to start somewhere, and if you want to, and it looks like the simplest thing to start. So not Gaussian, because most mathematical work is about Gaussian fixed points, but this is non-Gaussian fixed point. And so this is what I'm going to do in the rest of my talk. So this basically ends the philosophical part of this presentation. But if there are already some questions or objections to my philosophy, I'm happy to give more comments. Are there any questions? No questions. Can you hear me at least?
Yes.
Yes.
Sounds good. Okay, so let me, without much ado, describe our model. So our model is going to be a fermionic long-range theory, a fermionic mean field theory, which is perturbed by a weakly relevant quartic interaction. So I will explain why we chose this particular model, but let me describe the model first. So in terms of the quadratic action, the mean field theory is given by this section in the red box. So I have n spinless fermions, n real spinless fermions psi a. The kinetic term involves this non-integer power of the Laplacian, del squared to some power. And these fermion indices are contracted with the symplectic n by n matrix omega AB. So this theory has SPN global symmetry. And so the two-point function of this fermions, psi of x, psi a of x, psi b of y, is omega AB divided by x minus y to the power 2 delta psi, where delta psi is in mean field theory is a tunable parameter. Can tune it. So the fermions are spinless. So this is a non-unitary theory. The spin statistic is not obeyed, but for organization group control, the lack of unitarity is of no consequence. So we're doing Euclidean RG. So since it's not unitary, you cannot rotate to Minkowski, but for RG, it's not it's really of no consequence. So it's, on the other hand, it's easier to deal with spinless fermions. So this fermionic mean field theory is perturbed by SPN invariant mass and quartic terms. So I have a mass term, psi squared, and I have a quartic psi squared squared. So now, since delta psi is a tunable parameter, I'm going to tune it. So I'm going to pick delta psi equals d minus epsilon over 4, so that the quartic interaction is weakly relevant. So I'm going to pick epsilon small and positive, so that the quartic interaction, which is going to have dimension d minus epsilon, is weakly relevant. So this is the model. I would like to motivate various choices that we made here. So what are the reasons why this particular model? So why is this? Why did we choose mean field theory? Because for the simplest mathematical constructions, you need a weakly relevant interaction at your disposal, and there are only two ways to get a weakly relevant interaction. Either you can tune the spatial dimension, you can take a dimension equal 4 minus epsilon. But this way it's present, it's not known how to do randomization group rigorously in 4 minus epsilon dimensions. So in perturbation theory, we can do it. We can do Bootstrap in 4 minus epsilon dimensions as well, with some assumptions. But rigorous non-perturbative RG is just, it has not been done. It's not clear what it means. And so then we go to the second way to get the weakly relevant interaction is to tune the dimension of the field, delta psi. So that's the way we take. It changes the theory, of course, but at least it gives us control over the RG. So why did we choose fermions and not bosons? So in fact, as some of us know, there are very similar bosonic models where you take a bosonic mean field theory and perturb it by phi squared and phi to the 4th terms. This is something that many of us have studied under the name of long-range Ising models. And so, in fact, these long-range Ising models for weakly relevant quartic, they can also be studied rigorously. But their treatment is much more complicated than for the model that I'm going to describe here. And so why is this more complicated? This is going to become clear towards the end of this talk. So then, okay, why spinless fermions and not direct fermions? This is no particular deep reason. So it's basically just not to bother by spinor indices. And in fact, there's an old paper in mathematical physics paper by Gavetsky and Kupiainen from 1985, who constructed some similar fixed points for Gros-Neveu type models. And their work is something that inspired also our project. So the difference from our difference from them is that, okay, we are trying to be a bit more pedagogical and we maybe prove a few more things. But it's definitely, this paper by Gavetsky and Kupiainen was an inspiration for us. So then the number of fermions n is, as I said, is an even integer number of fermions. So we are going to take n larger than or equal to 4, so that this is necessary to have a non-vanishing quartic coupling. So quartic involves at least 4 fermions, so to do its vanishing. It's interesting to consider the perturbative beta function in this theory earlier on. So it's going to have the following form. So the beta function for lambda is going to have the classical term minus epsilon lambda, and it's going to be the first quantum correction with the coefficient n minus 8. So in fact, if you remember in the Wilson-Fisher theory, the one loop coefficient is n plus 8. So this is not accidental, because at the level of perturbation theory, the fermionic SPN model goes into the bosons if you change n by minus n. at the level of perturbation theory. At the level of at non-perturbative level, this is not true. So what we do fermions, so we get n minus 8, and at the one loop we get a fixed point with the coupling epsilon over n minus 8 for n not equal to 8. So the case n equals to 8 can also be done. So in fact, this vanishing of the one loop beta function at n equal to 8 is accidental as well. So that the two loop beta function does not vanish for n equal to 8. And for this reason, for n equal to 8, the fixed point coupling is square root epsilon. So this can also be done, but we exclude this case. So in our paper, we only consider n equal to n larger than or equal to 4 and n not equal to 8. So finally, the spatial dimension for us has to be an integer since it's rigorous, and we consider the case d equal 1, 2, or 3. So the reason why d equal 4 or larger d is excluded is that for d equal to 4, the theory gets another relevant local operator, which is del psi squared. And so as you will see, the relevant and marginal and close to marginal directions in this rigorous RG game, they have to be treated separately. And so this case, when new relevant directions open up, it can also be treated. So there's no difficulty of principle, but in practice, we exclude this case. So we would like to consider theories where only two directions are relevant, which is psi squared and psi to the 4th. And so in this setup, we prove 3 results. So we prove that this renormalization group flow has infrared fixed point for small epsilon. But we also prove that if you take small negative epsilon, then this renormalization group flow has a UV fixed point, because now the quartic direction is weakly irrelevant in the infrared, so there's a UV fixed point in this case. And we prove another thing, that actually you can also take epsilon a complex number, and the fixed point in this case exists for any epsilon in the complex plane in a small neighborhood of epsilon equal to 0. And the perturbation theory, so this has two consequences. So the first consequence is that in this theory, perturbation theory actually converges. So if you were to do the epsilon expansion in this theory, then you wouldn't need to do Borel summation. You could just sum the series and you would get predictions for critical exponents, at least for small epsilon. And another consequence is that the UV fixed point and the infrared fixed point are analytic continuations of each other, so without branch cuts. So these are kind of unusual properties of this theory, which are due to the fact that the theory is fermionic. And we will see later on why exactly this happens. So what's going to come next is that I will describe some technical details of our construction. But before I go into that, perhaps I should again pause and see if there are any questions.
I have a question.
So for the convergence, do you know what's the radius of the convergence?
Well, we did not invest effort to like follow through all the constants, but this can be done, but it's probably something like 100th or something. If you just go through all the estimates and you take all our constants at face value, then it's going to be something small, not astronomically small, not like 10 to the minus 6 or anything like that.
So it's a finite value.
100. But you know, the way these mathematical theorems are always work is that, okay, you can prove convergence in a certain radius, but then it's also possible, in fact, it holds in a larger radius. But so to see the convergence radius, you just have to compute the perturbative series, and then you will see empirically that the coefficients don't actually grow as fast as they will in bosonic theories.
Thanks.
Any other questions?
So these in the ON model, these statements would be true in some formal sense at large n. Is that right? So it's sort of like that case.
In ON model, it would be true at large n.
Or I'm asking, would this be?
But you mean that if you take large n and if you do an expansion 1 over n, or what kind of expansion would you do?
Say we work at leading order at large n, but then we look at as a function of epsilon.
Yeah, in that case, we know that the coefficients in 1 over n expansions are just some well-behaved function, analytic functions of D. Yeah, so they can be expanded in epsilon. In that case, there would be no problem at all. But to extend that result to finite n, I think it would not be possible in the bosonic theories. It's just even though the Bayer functions are related to each other by analytic continuation, n goes to minus n. There should be some miracle that for the bosonic case, the Bayer function coefficients will grow, and if you do this extend to n to minus n, they will just remain bounded so that the series will converge. This is interesting. So in fact, this phenomenon, as we will see, it's this kind of convergence of perturbation theory and fermions. It's not very well known in theoretical physics, but it's something that mathematicians have been discussed for a long time. So yeah, it was fascinating for me to uncover these things. Okay, so some technical details. So there are some, so when you start doing this realization group rigorously, so some things are exactly like, like you learned them in grad school. There is nothing particularly different, but some things are less standard. So let me describe, you don't have to relearn everything, but some things you have to get used to. So the standard things is that, okay, it's a Wilsonian RG, so you're dealing with an action with a UV cutoff. For example, let's set the UV cutoff to 1. And it's the usual RG steps. So first you integrate out, you lower the UV cutoff to lambda prime. For example, lambda prime equals lambda over 2. And then you rescale momentum so that lambda prime goes back to lambda. So that's the usual scheme. It's just like, as Wilson said, nothing changed here. So let me now describe the less standard things, the more characteristic of our model as well. So the first thing is that you have to work with a C infinity cutoff. So in physics, we like to work with a sharp cutoff often. But here you have to do with C infinity cutoff. So this means that when you take the modes which are integrated out, then they have the propagator of this form, chi of p divided over p squared to some power. And this chi of p is a bump function. So it's a bump function which is supported away from 0. It vanishes in some neighborhood of 0, and it also vanishes for large momentum. And so the reason is that if you do this, if you do C infinity cutoff, then in position space, this propagator is going to have fast decay. So we know that smoothness in momentum space transforms in fast decay in position space. So in fact, you can arrange that this decay be almost exponential. Okay, for example, e to the minus a constant x to the 1 minus delta. You cannot make it exponential because if it were exponential, then the cutoff would have to be analytic. But it's not analytic because it's a C0 infinity function. So it vanishes somewhere, but not everywhere. But you can arrange it to be stretched exponential, which is enough for our purposes. In any case, the stretch exponential decay is, compared to what you would get for sharp cutoff, it's very fast, because if you take a sharp cutoff, then in position space you would have some power law decay with some oscillations. So it would be a mess. So this really messes up your organization group scheme. But it's okay. I mean, so in fact, there is one classic paper by Joe Polchinski from 1984 who considered C infinity cutoffs. It's this famous paper, Organization Group and Effective Field Theory, which many of us have read. So I once heard the talk of Nimar Kanihamet, who said that that paper was the only thing which stopped him from quitting physics. But there's difference from what we do and what Polchinski did is that Polchinski did an infinitesimal organization group transformation, but we have to do a finite RG step. So in fact, infinitesimal RG transformation, it's good if you are interested in perturbation theory, but in non-perturbative RG, so far, if you look at the literature, it proved impossible to avoid dealing with a finite RG step. But okay, so we do a finite RG step.
Sorry,
So,
is it
yeah?
is it easy to understand why finite infinitesimal RG steps are out of control if you go beyond perturbation theory?
It's not super easy to understand why, but okay, I'll give you one reason. So you will see that there is a big difference between fermions and bosons. So for fermions, transition group step basically converges, and for bosons it doesn't. But at the level of Polchinski RG equation, it's very hard to see how. I mean, at the level of Polchinski RG equation is basically there is no difference between bosonic and fermionic RG. Okay, there are just some signs here and there, but you don't see why. Infinitesimal Polchinski RG equation behaves in exactly the same way for bosons and for fermions. While integrated Polchinski equation, something which gives you a finite RG step, miraculously behaves for fermions much better than for bosons. So it's just, but it's an interesting problem. In fact, I talked to many mathematical experts to see what is known. We have some comments in our paper about this point. Polchinski equation is much easier than the finite RG step. So if one can manage to make it work, it would be a huge simplification. So, okay, so then there's this something to be discussed is that in our theory, we have this dichotomy. So there's a kinetic term, which is non-local, it's a long range. And then we add these interactions, which are local, at least bare interactions. One could worry perhaps is that, okay, once you start doing RG, that perhaps something is going to happen and this non-locality also will penetrate the interactions. Also the interactions will become very non-local, but that actually does not happen. So in fact, the only non-local term remains the kinetic term. And this is kind of easy to understand is that, okay, even though the kinetic term is non-local, but when you take this fluctuation propagator, it has both UV and IR cutoff. And so when you construct the vertices of the next RG step from the previous vertices, so as I said, the propagator decays very rapidly in position space. So it means that the vertices that you will construct, they will have all, they will not be exactly local, but they will be, the degree of non-locality will be at most that of the propagator. So as we said, stretched exponential. So you will never get non-locality, which is power-like in the interaction vertices. And so whatever you generate at the RG step is never going to mix, is always going to be distinct from the kinetic term, which is long range. And so you will never renormalize the kinetic term by this sort of procedure. So in other words, in this model, well, this is a very well-known feature of these long-range models. So we discussed this in our work with Leonardo and Connor and Bernardo on the bosonic long-range models. So there are no wave function renormalization. And when the model flows from the V to IR, if there is an IR fixed point, then the dimension of psi at the IR fixed point does not renormalize. So it's exactly equal to the dimension of psi to V fixed point. All other operators like psi squared, psi to the fourth, and so on, they renormalize, they get non-trivial anomalous dimensions, but psi itself does not. So this is something which differs, where this model differs from the local models. So that's something that I just said. So in position space, permutation group generates terms which look like a bunch of psi's integrated against some kernel, which has some rapid decay at point separation. And so now you have a choice. You can take this kernel, and in fact, you can take this interaction term and you can Taylor expand, if you wish, in local monomials. Because if you take this, for example, here I did it for the term involving two psi's, we can take psi of x, psi of y, and we can expand psi of y around x in Taylor series. And so this will generate a bunch of monomials, and the coefficients of these monomials, which are given by integrals of h of x with respect to powers, they're all going to be finite, because h of x decays as a stretched exponential. So you could do this, but actually this is a very bad idea. So this is something which we do not do. This was this would be very inefficient, because it's actually, when you do this expansion, you lose information. You have this bunch of terms, they are in a very neatly packaged in these kernels, h of x, and they're all related to each other to this kernel. So if you expand them, you lose this relation. So for example, reassemble them back if you want. It's not immediately obvious. So it's better not to do this. So that's, by the way, one point where this non-perturbative RG differs from how its renormalization group is usually done in physics. So in physics, we always love to expand everything in monomials. So this is something that here we don't do. But okay, this is true, but there are two cases where a little bit of expansion is needed. So it's needed for the quadratic term and for the quartic term. Namely, let's take the quadratic term. So it's h of x, psi of y. What you need to do is that you don't need to fully expand it in monomials, but you need to extract from it the local quadratic term, psi squared of x. So to do this, you take psi of x and you expand it to first order using Leibniz-Newton formula, and so you get some other kernel h tilde mu times something which only involves first derivatives, d mu of x, d mu psi of x, d mu psi of y. And you have to do something similar for the quartic term. So the reason why you do this is that you think you know that your theory only has two relevant directions and everything else is irrelevant. So you have to separate these two relevant directions explicitly. So you have to, if you just dealt with this kernels, then it would look like you have, like for any kernel, you have a different relevant direction. It would look like we had infinitely many relevant directions, but it's not true. So only one of these directions, namely the local psi squared, is relevant, while all these other terms, since they contain derivatives explicitly, by naive power counting, which actually is rigorously, then remains rigorously true, that these terms are going to be irrelevant. So that's one case where you need to expand, but you only need to expand to first order. So it means that the final interaction terms that you have, they look like some kernels integrated against fields, and these fields are either psi's or first derivatives of psi's, but not high derivatives. So the high derivatives are never generated.
So a question about the irrelevant terms. You said that naive power counting is rigorously true. You mean all the way on the flow, so there are no like dangerously relevant operators that could cross and become relevant afterwards. If something is irrelevant at the beginning, you just know it's going to be all the way.
Well, you don't know it a priori, but this is why to show that this is indeed remains rigorously true, we need this small parameter epsilon. So we have this epsilon, small parameter epsilon, so all anomalous dimensions, they get corrections.
I see, okay.
And we can show that those corrections are small. So
small, I mean, not perturbatively small, but small in this finite small range. So epsilon doesn't need to be.
Small in a small and full range, epsilon less than epsilon 0, yeah.
I see.
Not asymptotically small, but in some small range. And how do we measure the size of these terms? So here, so I already mentioned the name Banach space. So we would like to package everything into some infinite dimensional space. So here we have to introduce some norms. And actually, we expect that these kernels are going to decay as fast as the fluctuation propagator, as a stretched exponential. And so this suggests, it turns out that a good norm to use is something which is called in mathematics weighted L1 norm. So we integrate absolute value of h of x against a weight function, and we pick this weight function commensurate with the expected decay. So since we expect a decay minus e to the minus absolute value of x, we multiply by e to the plus absolute value of x with the appropriate constant a, which we choose and keep fixed once and for all. And it's in this norm that everything is going to be controlled, that everything is going to be small or large or convergence is going to be in this norm. Okay, well, then the final, not the final, but the next step is to discuss the expected size of interaction terms. So we have this small parameter epsilon, and we have infinitely many terms, and we have to kind of get an idea what is the expected size of these terms. And that's something that, okay, that any of us would easily do. So you just kind of say, well, let me just pick the lowest order Feynman diagram which contributes to that or that, to this or that term, and that's kind of, the term cannot get smaller than that. So you have to look a little bit what are the lowest diagrams, and you quickly understand what is the scaling in epsilon. Then of course you have to show that the scaling remains correct, including all the other contributions, but this naive guess turns out to be correct. So the lambda and nu, the quartic and the mass, their size is going to be fixed by the lowest order one loop fixed point equations, which predict that lambda is over the epsilon and nu is also going to be over the epsilon. Since we are dealing with the Wilsonian RG scheme, the fixed point mass is not 0 as it is in dim-rag, but it just takes some finite value which is over the epsilon in the units of the UV cutoff, which we set to 1. Then all the, then you have various various other terms, various interactions, irrelevant interactions, and they all have higher scaling than epsilon squared. Okay, I mean, I don't want to go through all of them. So there is a non-local H2, the non-local H4, which comes from this diagram. So it's all very, very intuitive, and you can understand it yourself without. So it's some very high for some interactions with high legs. It's this kind of comb diagram, hair comb diagram, which contributes, where you just put a lot of quartic interactions all together. So this gives you a certain scaling epsilon to the k. So these are the scalings that you guess they have to be correct. And so now you are in a position to form a Banach space of interactions. So interaction is going to be a sequence of, so the action, let's say the full action S of psi is going to be parameterized by nu, by the mass, by the quartic lambda, and by an infinite number of these irrelevant interactions that I introduced. And so what you do is that you divide every one of these interactions by appropriate scaling in epsilon, so that they are all of the same order, and you take a maximum of all of these terms, a sup of all of these terms, and this is the norm of your full interaction, in which you want to control everything. So a little bit of functional analysis, but not too much. And so now, okay, so this is our parameterization of the interaction. So we can write down a realization group map in this space. And so this is just notation. So I separated explicitly the one loop RG for the mass and for the quartic coupling. So these are one loop RG coefficients that we have to evaluate. So I mean, they're given, they take this coefficient B takes exactly the same value as you would compute it in DIMRAG. You can, as we know, the one loop RG coefficient, it's realization group scheme independent. And, you know, and there are all these functions, nonlinear functions in nu, E lambda, and EI, which involve contributions of all other Feynman diagrams, of infinitely many Feynman diagrams that you may write. And so these are some complicated nonlinear functions on your Banach space. And you have to show that these functions satisfy a bunch of properties. I mean, to begin with, that these are finite functions, that these functions are defined by some series and they're convergent. And they also, not only do they have to be convergent, but they have to be bounded, and well, satisfy a bunch of things. So actually, so most of the work goes into showing that these properties into these functions EI. But once you prove the properties of these functions EI, then what do you do? So you have the fixed point equation that this realization group map that I call R, and S is the interaction, S of psi. So the fixed point equation just says that R of S has to be equal again S. So this fixed point equation has to be solved in your Banach space, but we don't work in the full Banach space. In fact, we work in a small neighborhood of the one loop fixed point. So from the one loop realization group, when you set all the relevant couplings to 0, you know that nu lambda is equal epsilon up to some coefficient, and nu up to some coefficient. So you pick a small neighborhood of this one loop fixed point, and in this neighborhood, you show that this fixed point equation has a solution. And to do this, you use, well, the classic theorem of functional analysis, which is called Banach contraction principle. So let me remind you what Banach contraction principle says. So you take a map F, which acts from a ball in a Banach space to itself. So from X to X, where X is a ball in a Banach space. And in addition, you impose that this map is a contraction, which means that if you take any 2 points, V1 and V2 in the ball, and you apply to them this map F, then the distance between the images F of V1 and F of V2 is smaller than some constant alpha, which is less than 1, times the distance between the points V1 and V2. So under this condition, you can show that for any initial point V0 in the ball, if you start acting on it with this map F, so you take V0, F of V0, F of V0, then the sequence is going to converge to a unique solution of the fixed point equation V equals F of V. So that's the Banach contraction principle, but we don't actually apply this Banach contraction principle to the renormalization group map itself, because the renormalization group itself is not contracting, is not fully contracting. It's contracting along all infinitely many irrelevant directions, but there is one direction, which is the mass, which remains relevant at the infrared fixed point. So you have to correct for that. And the way to correct for that is to use a version of Newton method. There is a variant of Newton method. So you construct from renormalization group map another simple map just by taking some linear combinations, subtracting things, and that other map is contracting. So when you activate it and it converges. So so actually, there is just one more thing to be discussed, and that's how you control the RG map.
Sorry, Slava.
Yeah.
Could you please go back to the last slide?
Yep.
Last one, the contraction. Okay, so in this contraction in the equation, so in the first equation with alpha equal smaller than 1, do you think it's possible? I guess it's possible in general the alpha should depend on the momentum in the RG flow, right?
Alpha should depend on what?
On the momentum in the RG flow.
On momentum and RG flow.
Yeah, when we do the Wilsonian RG flow, we introduce a cutoff. So this alpha, or do you think this alpha is a constant universe? Is it a general, is it a constant or momentum dependent factor?
No, it's not momentum dependent because I already eliminated all momentum. There's no momentum. So there was lambda, but lambda was set to 1. And then I go from lambda to lambda prime, and then I rescale back to lambda. So this is one RG step.
Yeah.
So I don't.
Yeah, I mean,
I always work in the same range of momentum as a result.
So for lambda, I mean, if it is, I mean the lambda. So the point is that here is alpha lambda dependent or not?
Well, lambda is set to 1, so.
So maybe I can ask you the question another way. So in another RG flow, so at a different point on another RG flow, the alpha could be different or the same as a constant.
Eugene, I'm sorry. So I just stated Banach contraction principle. It's a general theorem about Banach spaces.
Yeah.
It does not apply to RG flows or anything. It's just a theorem of Banach space. But this Banach space has some norm, some distance. So constant alpha is the same for any V1 and V2. So in the Banach contraction principle, alpha does not depend on lambda because lambda doesn't enter anywhere.
Sure. I mean,
so in our case, I introduce a Banach space. So my Banach space was introduced like this here. So this was my Banach space, this norm on S.
Mm-hmm.
So as you see here, also there's no lambda. So lambda has disappeared. I mean, by lambda, you mean small lambda or big lambda?
I mean the big lambda.
Big lambda,
I set
it to 1.
Or the energy scale of the generalization.
But
yeah.
I think we are talking about different. So in when you do RG fixed point equation, you only have to apply RG once, right? Because RG equation says S equals R of S. You don't have to apply R several times. So lambda, the scale lambda, doesn't have a chance to change much. It's just like from 1, it goes to 1/2, and it goes back to 1 immediately. So it's not like I apply renormalization group several times and see what happens. I don't do this. I apply renormalization group only once, only one step.
Yeah, yeah.
I think we are thinking about different things. So
Yeah,
you imagine that I start applying, that I consider the full memorization group trajectory, that I start somewhere in V and start acting with memorization group many times until I flow somewhere in the IR.
yeah, exactly. That's what I thought.
That's something that could be done, but this has to be done if your goal is to construct the full memorization group trajectory.
Yeah.
But that's not what I'm discussing now. What I'm discussing now is just the fixed point. And to discuss the fixed point, I only apply the group map once.
Okay, thanks.
At any scale. It can be done at any scale. Fixed scale 1, apply memorization group at this scale, and look for an action at this scale which is preserved by the memorization group.
I have a question.
Sure, David.
So you chose this factor of 2 for the renormalization group step. Could this be done for any finite factor bigger than 1?
So in fact, we have several methods to prove things that you prove. For some of these methods, it can be chosen any number larger than 1, but it has to be strictly larger than 1. And for other methods, it actually has to be chosen sufficiently large, so that the 2 wouldn't probably do it, like it has to be 10 or something.
Sorry, wait a minute. So you're saying in reality you actually need something bigger than 2?
Yeah, for some of the things that we do, we need it larger than 2.
Ah, okay.
Which is a bit annoying, but that's life.
So the 2 in these slides is for illustration purposes.
Exactly.
Okay.
Exactly. But there are other things that you can do where you can pick at any number larger than 1.
Okay, thanks.
Sorry. May I ask? I'm a bit lost at some point. What's the definition of this UI? I thought after renormalization you got some non-local functions, and how do you define this UI?
UI is a function. So UI is any of this function H2,
okay,
H4, H6. It's any of these functions. So it depends on several parameters, on several coordinates. Sorry. So in fact, you see when you apply dilatation to UI, you have to rescale its arguments. So you replace the arguments x by 2x.
Ah, I see. Okay, I see. Yeah. Thank you.
Yeah, I realize it's probably too schematic. But, thanks for your questions, guys. So this is the last and crucial point, which explains why we do things for fermions and not for bosons. So as I said, renormalization group map consists of 2 steps, which are completely standard. First, you integrate out, and then you rescale. When you integrate out, you have to construct the effective action, which you construct by using Feynman diagrams. And the number of Feynman diagrams, as we know, is very large. It's superfactorial, and it's superfactorial for bosons, and it's also superfactorial for fermions. It's exactly the same number of Feynman diagrams. While the factor that you gain is 1 over n factorial, so it's not in nth order of perturbation theory. So perturbation theory, for this reason, diverges for bosons. But for fermions, actually, there are partial cancellations between diagrams of the same order because of fermionic signs. And as a result, perturbation theory for fermions converges at small coupling. So this is so this fact, it goes under the name of fermionic sign blessing. You have heard about fermionic sign problem, which is the reason why fermions are hard to Monte Carlo simulate. But here we have a fermionic sign blessing. So they're hard to simulate, but they're easy to compute in perturbation theory. And in fact, physicists who work in condensed matter physics and compute things in perturbation theory for fermions, they know this empirically, that if you evaluate tons and tons of perturbative coefficients for fermions, you see that things converge. But you still have to sum up lots of terms. But for mathematicians, actually, in mathematical physics, there are some pretty amazing combinatorial identities which make this constellation manifest. So this constellation is, if you just think in terms of Feynman diagrams, it looks like a miracle. So in theoretical physics, we would say, okay, we have in the nth order of perturbation theory, we have lambda to the n over n factorial, and we have now to sum over all connected diagrams to get an effective action. And there are 2n factorial of such connected diagrams, roughly. But in mathematical physics, they came up with ways to take this series and repackage it, like partially resum it in a combinatorial way, so that the same sum looks like, instead of summing over connected diagrams, so you still have the same vertices, but you sum over connected trees connecting these vertices. And the number of connected trees is much smaller than all connected diagrams. It grows only as n factorial. So the sum only has n factorial terms. And the things that you sum are some disconnected endpoint correlation functions, which with some weights which are smaller than 1. And if you're just doing the theory of bosons, then this resummation doesn't help you much, because these disconnected correlation functions, they still grow as n factorial. But in fermionic theories, at this level of disconnected correlators, you can rewrite it as a determinant, and you can show that it's smaller than some constant to the power n. And so lo and behold, we have n factorial divided by n factorial times c to the n, and so the whole thing is going to converge at small coupling. So when I started doing these things, then, okay, I learned about these formulas from Alessandro and Vieri, but I have never seen them before in all my life as a theoretical physicist. And so I got a bit flipped out when I first saw it. And I think that this sort of formulas, they should be more widely known. And in mathematics, they're usually used to prove certain things, that certain things are bounded or certain things that converge. And that's how we use them also in our paper. But I think that these formulas, they should be more widely known, and I think they could probably be used also to compute some things, not just to bound them. So if you're curious, then the keywords are Bridges, Battle, Federbush formula, and Graham-Adamar bound. So we review it in our paper in a pedagogical way. You can also read about this there. But with these formulas, armed with these formulas, then we are basically done. So we can control the one step of fermization group, and we can show that all the properties needed to apply the Banach fixed point principle, Banach contraction principle, are satisfied. So that all the inductive assumptions that you make on your effective action, that certain things are smaller than epsilon to some power, that they remain true also after the RG step. And so that on top of that, you have contraction along the irrelevant direction. So if you start with a good approximation to the fixed point, like just with the one loop fixed point, and you start applying this RG map recursively, dressed with these factors which make it contractive, then you will just converge to the true fixed point in this line. And moreover, after n steps, so if you don't want, of course, to converge, you would have to go infinite, you would have to apply it infinitely many times. But the nature of this result is such that if you only can afford to apply this k times, then you still know that the error that you know how far you are from the final fixed point, because of this constant alpha in the Banach contraction principle. It tells you how fast you are converging. And so since we know what this constant alpha is, we know how far we are from the final fixed point. So even if you apply it only k times, you still get some rigorous approximation result. So I'm not saying that what we did is like practically useful. At the moment, it's just another theorem, but it does, I believe it does point a way to how perhaps this can be made in the future practically useful. So this basically brings me to the summary. I tried to motivate that even though in the way people do non-perturbative RG in physics is indeed, it's true that, you know, when the fact that many physicists distrust non-perturbative RG, it's justified, because indeed in physics it does involve uncontrolled approximations. But it's the problem of implementation. It's the problem of people who implemented this non-perturbative RG in this way and not in any other way. And it's not true that if you read some literature about non-perturbative RG, you say, I mean, you see there that people say, but of course you have to truncate. There's no other way to make progress. It's not true. It's the problem of implementation, not of the idea. And rigorous mathematics literature, it gives us hope that much better implementations can one day be found. And in this paper, we have to start somewhere. So we started trying to bridge this gap between mathematics and physics literature. And we described what is perhaps the simplest optimization group fixed point. So that perhaps for people who, like me, have been very afraid to by this daunting math literature, so perhaps provides a convenient entry point. So this is what we've done, and I would like to finish this talk with this wide open problem that that we should find a non-perturbative Fermi group fixed point of the three-dimensional easy model, and we should use it to compute the critical exponents with rigorous error bars. I believe this can be done. Thank you.
Questions?
Yeah, can I ask a question about this, the open problem, perhaps? So how important, it looked, well, I mean, I'm sure I lost some stuff, but it looked important for you to have epsilon, so to have a good starting point where you're sure you're close to the fixed point, so then everything works and everything is under control, etc. Even more than having everything converging. I mean, that's also important, but I mean, if you're already close to a fixed point, then maybe you can do something. But in the 3D easy model or any flagship non-perturbative fixed point, that's sort of by definition not at our disposal. So why are you optimistic?
Well, well, to tell you the truth, I did not really explain the reasons for my optimism. Well, I can give you two reasons. So the first reason is I can give you two ways how one could try to get at this non-perturbative RG fixed point. The first way would be to try to understand better this non-local models. Suppose that we learn to do bosonic models in this language, and we learn to compute this fixed point for small epsilon for bosonic models. So if you know it for small epsilon, then little by little you can start increasing the range of epsilon. So you know where to look. And as we know, this long-range Ising fixed point at some critical epsilon, it crosses over to the short region fixed point. So if you manage to get to this very large value of epsilon, then you're done. That's that maybe is not very realistic. It looks hard. But in general, there is another way to do this kind of things. So why did we do everything? Why did we need the epsilon parameter here? So we needed the epsilon parameter to find this initial approximation to the fixed point, and then to prove a bunch of things. But there are some situations in mathematics where people have given so-called computer-assisted proofs for various things. Well, one of the famous examples is the problem of the Feigenbaum constant. So that's something that I'm also quite inspired about. So the Feigenbaum problem, the problem of the Feigenbaum universality, it's a problem of dynamics of composition of functions. And actually there is some functional equation that you have to show that that has to have a solution. And then there is also some notion of RG and some critical exponents, and the Feigenbaum constant is such a critical exponent. So the way people showed eventually that it exists, this constant and this fixed point, is that they use the computer to find a good approximation for this fixed point with some number of digits. And then once you know a good approximation, which you find using the computer, then you can actually show that working in the neighborhood of this approximation, you can make a finite computation that shows that all the properties that you need to claim that things are contracting, to apply the Banach contraction principle, they're satisfied. So this is called computer-assisted proof. And so this has been done in some cases, and perhaps it can be done one day for the three-dimensional Ising model as well. So one should find some smart computer way to find this approximate fixed point, and then to upgrade it to a rigorous fixed point. But you know, the upgrade to the rigorous fixed point only is needed because if you want rigorous error bars. Otherwise, you can say if you find the computer method which already gives you an approximate fixed point, maybe you, as a physicist, you will say, well, I'm satisfied with this.
But, I have a question about this norm on the kernels that you used. So the norm involved this e to the absolute value of x to the 1 minus delta factor times a. And so the things that have finite norm in that norm are, as you said, these kernels with fast decay. And if we were sitting at a conformal fixed point, why don't we expect to see kernels with power law decay appearing?
Well, you must have some different intuition from mine, because I kind of internalized that in our procedure, this assumption of exponentially fast decay, it's self-reproducing, because if you have some kernels which have exponentially fast decay, you contract them with with these propagators, which also have exponentially fast decay. Now, I think your question is, what if you take this exponentially fast decay, you contract with exponentially fast decay, but then after kind of maybe this exponential decay will degrade. Maybe that's this is the question. This decay, but it doesn't degrade. It doesn't degrade because of this dilatation operation. So here, as I indicated here schematically, when we rescale, so we had the kernel UI which had some decay. So if you rescale x to 2x, then you get a kernel which has an even faster decay. So in fact, this dilatation, which kind of makes things a bit more local, it fights against the degrading, so that this assumption of exponential decay, in fact, is self-preserved, so it doesn't degrade. So this is what happens at the technical level, and I'm not sure I have a better answer.
Well, I guess it's just, yeah, I mean, so if we were to look at the fixed point, then we have some set of kernels. And it's interesting that these kernels all have length scales in them, even though we're at a fixed point.
Exactly.
I don't know what to make of that.
It's an arbitrary, yeah, it's some sort of arbitrariness. It's some sort of dirtiness of RG. It's hardly, well, actually, I was expecting a different question. I was expecting why people would say, why is it that the fixed point action is not local? Because I have this exponentially decaying kernels, but so that means that the action is not exactly local. I did not discuss this, but if you were to introduce the scaling operators in this picture, so I did not discuss here the perturbations around the fixed point, but one could, we don't do it in our paper, but it's some problem for the future, to discuss what happens if you perturb the action. And so you would like to find some eigenperturbations, as we usually do in RG. So those eigenperturbations, they correspond to local CFT operators, but they will also be given by some kernels with exponentially fast decay. So they're not going to be exactly local.
That's
so
interesting.
Now it's really weird, because we have a non-locality of the interaction, and we have non-locality of the scaling operators, and somehow they will have to exactly cancel to produce us the cherished CFT rules of OPE and operator state correspondence when operators are inserted inside the sphere. It's really, it's really mysterious how this is going to happen. Well, we discussed this in the conclusion section of our paper, but this has never been done not in math literature, and this is basically an interesting problem.
So so the length scale, if we sit at the fixed point, then we have a length scale in all the kernels and also in the scaling operators. And that idea is that that length scale can be chosen to be whatever we want, I guess. But it has to be there to write the formulas.
This length scale is the cutoff scale, because we are writing our action at the cutoff lambda with so which we set to 1. So everything is set. So our theory is our action is a fixed point action, but it's written at the cutoff scale. So this cutoff scale is everywhere.
Mm-hmm. I see, but because it's a fixed point, we can change the cutoff and we get the same theory.
Yeah, so I guess it's easy to see that that the correlation functions they scale as power laws because of this. It's relatively easy to see.
What happens if you tried to look at a correlator of, say, scaling operators where they were closer together than the cutoff? Would you just get a divergent series?
No, I think the correlation functions of the scaling operators are going to be exact power laws. So that's something which we had big discussions about, and it's not something that we fully understand. And I agree that it's confusing, but basically the idea is this. So if you just take field psi, for example, then psi has the UV cutoff lambda. So its 2-point function is not going to be an exact power law. But we say that there should be some scaling operator. Okay, this is what classics taught us, is that there should be some scaling operator whose correlation functions are exact power laws, even in the cutoff theory. So you say, how can this happen? Well, it happens, I believe, because this problem exists, by the way, even for Gaussian fixed points. So the way this is resolved, I believe, is that your scaling operator is kind of finite series, psi plus psi cube. Not only do they involve kernels, but it also involves some operators with higher powers of psi plus psi cube plus psi to the 5th and so on. And these higher powers of psi, they have momenta extending in the UV larger and larger. And so when you construct the scaling operator, it actually has a chance to have a correlation function, which is an exact power law at all distances from 0 to infinity.
So has this been constructed in Gaussian fixed points? Just as an example?
I'm not aware of this.
Oh, I see.
It's amazing. It's amazing that these things have never been done explicitly. It's part of the reason is that mathematicians, they actually don't like to think much about these fixed points. They like to say, oh, well, I proved the theorem about, some lattice model which flows somewhere. So that they can explain this to statistical physicists, something like that. But even though we physicists believe that the fundamental thing is a fixed point, that's what governs everything, there's actually not much literature which just like, okay, let's just forget about all the details, let's just study the fixed point and that's the end of it. Somehow this is not seen as the right question to ask in the math literature, to my amazement. But if you read classics, if you read papers by Wilson, Wigner, that's what tell you. There are scaling operators even in the cutoff theory, and their correlation functions are exact power laws. Take it or leave it.
Okay, thanks.
But these 6 points are conformal field series, right?
These fixed points are supposed to be conformal field theories for the same reason as the longer range Ising, like bosonic theories, are believed to be conformal field theories.
So let's take dimension to be equal to 2. I believe in that case, you have a sort of, better understanding of the two-dimensional series. So in your example.
No. Because these conformal theories, they are non-local, so they only have global conformal invariance, even in 2D. So they don't fit the usual. There's no stress tensor, there's no Virasoro, there's only global conformal invariance in higher D and in 2D.
So if I understand your talk correctly, so you're saying that based on this theorem, a fixed point theorem, you can show that there is such a conformal field theory, as the fixed point of the theory you constructed. Is that?
I can show that there is a fixed point, but now once we know that the fixed point exists, there is a long list of properties that you would like to show that this fixed point has. So based on physics prejudice, like for example, one of its properties is that it should have the global conformal invariance in any.
Okay.
That's something that we have not shown. It's an open problem. But I believe that this since it's the simplest fixed point, in my opinion, it just means that all of these folklore properties of fixed points that we know and love, they can be explicitly demonstrated in this example once and for all. So I think this will be very, very, very satisfactory. So my main motivation in this whole business is that I hope that this will lead to new computational techniques in field theory. So I'm not, I'm excited if if one can explicitly prove some things, but only that much, because my next step would be to start computing something. But I hope that there's going to be some people out there who are more interested in structure results, and hopefully they will clarify these things and see how.
Yeah, but so this I just want to ask, so this fixed point theory would also be non-unitary, right?
It will be it will not have reflection positivity.
Okay, all right, thank you.
Anything else? Okay, thanks Slava again.
Thanks, Tom. It was a pleasure. See you all.